And hello, welcome to this video of Lammps. Okay, so last time we just talked a little bit about how to install Lammps. Okay, now next thing we're gonna try our hand at running some cases. Now, if you go to your Lammps directory, which is here, and as you notice, I am running my Arch Linux Docker container, and I am inside this lamp stable directory. As you would see, the examples are over here. Okay, the examples are here. Now, first thing first, you will notice that again, it's a very huge overload of data. You don't really know where to start, right? So how do you know where to start? Okay, so if you want to look at what's where to find your tutorials, okay, and which tutorials are pertaining to what, okay, go to lammps.org. There's a documentation that actually has this tutorials thing here. Okay, now you go to the Lammps tutorial. You can go to this part saying simple Lammps examples. Okay, again, go to Lammps tutorial and go to this part saying that is called simple Lammps examples. Now you click on this, you'll be directed to a nice PowerPoint slide by Mr. Plimpton. Yes, if I'm I don't know how to pronounce the name properly, or Steve here, from Sandia. So Lammps is done by Sandia. This is a workshop. Okay, now it's on site. The PowerPoint slides are here for you. As of the time of this video, it was 7 years ago. All right, so let's take a look at this slide. It says that there are a few simple cases we start with. Okay, and then the first line here, it says the examples README has one-line description of 30 examples. So let's go to the README. Okay, the README is actually over here. So you can just do a quick Vim README. Okay, I assume you know how to set up your Vim to whatever you like. So you do a Vim README, it says here, okay, these are Lammps example problems. So yeah, so you will find all sorts of the Lammps example problems here, along with each of these input files. Now, here it says there are 3 flavors of subdirectories in this file, each with sample problems you can run with Lammps. Okay, so the first is the lowercase directories. So these are simple test problems for Lammps and its packages. So if you take a look, for example, colloid, comb, controller, all of these are lowercase directories. Okay, so these are simple test problems for Lammps and its packages, whereas the uppercase directories, these are more complex problems. Okay, so the uppercase directories are, for example, a sphere, there's a big one on heat, and then there's another one on units. Okay, the last one is technically an uppercase directory because user is all in uppercase, but yeah, this is actually probably where you want to put your own custom files here. Okay, so if you have your user files, I guess you would sort of put it here. So these are, I guess, custom directories. Okay, but you'll have many cases here as well, and they all seem pretty complicated. Okay, so these are tests for user packages. Okay, if you're just starting out, I recommend you leave these 2 out and you just go straight for your simple case directories. Okay, so at least let's yeah, once we look through these example problems, we find that the lowercase directories are where you can find the simple beginner problems, right? Simple beginner problems. Okay, so let's take a look more in detail. It says here, under the lowercase directories here, each of these subdirectories contains a sample problem you can run with Lammps. Okay, most are 2D problems, so they can run quickly. So just ignore all of, you can read this all yourself. But yeah, these lowercase directories all have a very simple description. So for example, the accelerate subdirectory will use all the various accelerator packages. Atmosphere ATM. Well, it's not atmosphere, it's Axelrod Teller Potential. Okay, body is body particles. Comb. Comb is not, talking about the comb that you used to comb your hair with, but it looks like these are models using the comb potential. Okay, and then there's an interesting one. If you're talking about fluid mechanics, you have Couette and Poiseuille flow. Again, I don't know whether I'm pronouncing it right, but well, you just have to know what these are actually referring to. What is Couette flow? What is Poiseuille flow? Not can go and just do a quick revision. Sometimes I forget also, because these are named after scientists. Okay, here's one that has for sodium chloride. There's melting, and there's one that uses Python packages as well. That's called Python. Yeah, this will be pretty interesting if you want to use the Jupyter notebook. So there's the Python package, and something a little more down to earth here. It's called the pour. Okay, pour is actually pouring of granular particles into a 3D box, and then using of the shoot flow. Okay, I think everything else is yeah, these are very niche cases which you will have to know what you're looking for in order to go and check them out. So yeah, this is how we do the labs. Okay, so this is what we are doing here. Okay, all right. So anyway, now that we have at least gone through a little bit of the examples README, let's go through some of the common problems. Okay, so in this slideshow anyway, there are first one is called colloid particles. Colloid particles, if you do a quick Google, according to this annualreviews.org, these are actually small particles that are suspended in a fluid phase. The size range is between about 10 nanometers and several microns. This makes them small enough to be suspended in fluid by thermal motion. So these are what colloid particles are. So if that's part of your work or research, that's what you probably want to start looking at. Okay, the next one is crack propagation. You have flow, friction, indent. I don't know how to pronounce this. All this. The other one's obstacle, pour, and shear. Okay, so if you want a very down-to-earth example, I guess the first thing you would want to look for is the pour, where you're like pouring granular particles into a box. And interestingly enough, this slideshow actually tells you stuff of how to what each case actually talks about, and there are some nice visualizations here. For example, this Couette and Poiseuille flow. This is basically, I think, 2D flow of some sort. Okay, both of these. There's a friction problem where you have friction on a micro scale, and I guess you just slide the plates on top of each other, and then you have these two ball hemispheres actually rub against each other. It's an indent problem, but let's go to the pour problem. What's the pour problem here? These are actually granular spheroids in a box. Okay, so what are the forces between each sphere? Okay, the forces between each sphere are in a normal direction, where I think you have normal contact force. Okay, you have normal contact force and also some tangential friction when spheres rub against one another. And overall, gravity will be acting on them, so it's really just spheres in a box. 2D version also exists. Okay, it's very interesting. Okay, upper and lower boundaries are done by this fixed pour command. and fixed wall gran command, something like that. Okay. Some options to play with are the size of the system, timescale of pore, direction of gravity, and to the input. Okay, so suppose we just want to get started. What do we want to do? Okay, maybe we want to start by playing around with this pore problem. So maybe we'll make our own custom directory, and then we'll copy over the files, the input files from the pore problem, and then we'll start taking a look at all of them. And of course, last but not least, we want to visualize, because I mean, it's nice to modify our stuff, but we can't visualize what we want to see and extract the data that we want to get. There's not really much point doing Lammps simulation. Okay, so let's this is the pore problem. Okay, so where's the pore problem? Okay, it's a little bit hard to see here because there's so many cases. So just type cd and you put pore. Okay, then you do a tab complete. If you don't have tab complete in your arch, you can pacman-s bash completion. Okay, so you will have these, you'll be able to install this. Okay. Okay, so you can install bash completion in arch. Okay, so once you do that, I believe you should be able to your various tab completions in time. Okay, so this is where your pore thing is. Okay, so to run it, very simple. Use lmp in the dash input in.pore. Okay, and the thing should take about half a minute to finish. So if you take a look here, the first thing it does is to create some orthogonal blocks. Okay, you have some particle insertion of some sort and all of this. Okay, then you'll see some sort of time steps here, and then it will just output some data. Okay, so you have a few time steps. So there are two parts of this simulation, right? There's a shoot flow, there's a pouring, and a shoot flow that comes after. So this thing, true enough, it took about half a minute to finish. All right, so if you want to take a look at what the input files are, you can go vim in.pore. Again, it is there are lots of information here which you may or may not be that familiar with, but let's try to start making sense. Let's try to start making sense of all of this. Okay, so for one, we have some useful comments here. The first comment says pour granular particles into chute container, then induce flow. Okay, so the first thing is to, I guess, initiate some atom styles and everything. So I guess this part I don't really want to touch just yet. Okay, but if you want to know what are the pieces that are interacting with each other, then you can look at this thing called atom style. Okay, all of this, well, if you're not sure, there is a guide. There is a guide that can tell you where these commands can be found. Okay, but I'll go through them after going through the comments. So let's take a look at the second comment. It says an important note: these values of stiffness and time step used in this example file produce a quick simulation and movie. More appropriate values for realistic simulations would be k equals 2.0 times 10 to the 5 and dt equals 0.0001, as in bench.inShoot. Okay, so there is this case called bench.inShoot. So if we go to bench, okay, let's go user, or maybe I'll go grep grep dash of grep dash r in dot shoot. Okay. Oh, they're only here in the PAW button, so the PAW files. Never mind. So anyway, forget it. Okay, so this is these are the proper time steps. But what could k mean over here? Well, let's take a look at the next line. It says pair style is gran hook history. Then you have this 2000 null 50 null 0.50. Now, if you just look at this thing here, chances are you're going to be pretty confused. But if you have studied physics before, you should know what Hooke's law is. These are laws of spring. Okay, the force exerted by the spring in this regime, elastic regime, it will be like F equals to kx. That is Hooke's law, where k is this stiffness constant over here, which is in this case is 2000. So I guess you put k over here in this 2000 category, and I guess the pair style here will talk about the interactions between each sphere, so to speak. All right. So, and the next easy thing to figure out based on this comment is this time step. So time step here is time step. You know, if you have a very stiff spring, like a very high K, you need to use very small time step. If not, your simulation will become very unstable. If you are familiar with simulations, you should know that the stiffer the problem, the more fine your time steps need to be. It's a stiff ODEs. Now, before we go on to more to look at all of this, if you take a look at this is actually the visualization step where you actually dump and output data, and you put them in a way to sort of like generate images. And we don't want to touch that just yet. We want to get ourselves slightly more acquainted with a few of these commands, at least the pair style and time step. And time step is pretty obvious, right? So let's just look at the pair style. Pair style commands, because that can actually change the way spheres interact with each other. Now, so what? Let's go through the commands. Okay, where do we find where do we find documentation for these commands? Okay, go to the Lammps website. It's called docs.lamp.org. So if you go to lamp.org, you can actually you see this page, lamps.org. Go to commands, and then you will go straight here. Okay, the first box over here should contain this thing called pair styles. So you can just right click, and you will be right there in pair styles. Okay, under pair styles, you will see this thing called pair style potentials. Say these are all the Lammps pair style commands. Some styles have accelerated versions. These are indicated by additional letter in parentheses. Okay, so for example, G equals to GPU, I equals Intel, K equals Cocos or something, O equals OpenMB, T equals OPT. So you see all this O, GIO, and all GKO, all these little things in the brackets. These are talking about acceleration. Now let's go to what we have in the. We'll try to look for this pair style. It says gran hook history. So let's look for gran hook history. Yeah, so gran hook history is right over here, and these happen to be having the letters K and O. K as in for Cocos, O as in OpenMP, so we can use OpenMP for this. Okay, this is a pair style gran hook history. All right, so the gran hook history is over here. Right, and now we can find we can see the syntax. So the first thing you do is pair underscore style. Style is over here. You can type in gran /hook, gran /hook history, or gran /hertz history. Okay, I'm not going to distinguish each of them just yet. But let's look at this thing. The next thing you have to put in is this kn. Okay, kn is here. This is the 2000. This is the elastic constant for particle repulsion force. So this is force per distance unit or pressure units. See discussion below. So you can see the discussion below for this. Looks very complicated, but at least all the documentation is here. You know what these are talking about without having to go into the source code and try to figure things out yourself. Okay, so next thing is here KT, elastic constant for tangential contact. Okay, so in this case we have a null input, so we don't have that elastic. Gamma n, so I guess n here you can think of it as k for the normal, and t is for tangential. So gamma is a damping coefficient. So damping coefficient for collisions in the normal direction, 1 per time unit or 1 per distance units. So this will be this number 50 over here. Gamma t is the same thing, but for the tangential direction over here. Then this next number here stands for this XMU thing, which is a static yield criterion. Unitless value between 0 and 10,000, or 1 times 10 to the 4. Okay. So this is this one here. And the last one is called is XMU. So KT, so this is gamma n, gamma t, the XMU thing, and the damp flag. Okay, damp flag is do you want to include tangential damping force? Okay, and this one is optional, apparently optional, because you have this keyword equals to limit damping. Okay, so I think that's all I want to talk about for this video before it gets really long-winded. But at least we covered, where are we supposed to find our tutorial files and what this pair style thing is over here. Okay, you can find it inside the Lammps documentation, no problem, and there's a lot of detail that goes on in here. You can see. Okay, I think that's about it for this video. Thanks for watching. See you guys again. Bye-bye.